Okay. Good afternoon, everyone. So I'll be presenting. Okay, maybe start the time. So this is the title of my talk, but basically I'm going to present work related to development of a code called G2C3, which is basically used to simulate plasma in a fusion reactor. And this work is done at IISc with Animesh and Joydeep, who is a student, as well as IPR from Ahmedabad. And to start with, I should thank the organizers as well as the funding agencies. So what's the problem? So basically, if you look at currently, we have only sun as the working fusion reactor, whereas we have been trying to build this tokamak fusion reactor since 50s. If you look at it, the gravity is the one which holds the sun together. But here in these particular in lab experiments, we want to use magnetic field as the one which confines the plasma. So the basic idea is that if you have a magnetic field, the charged particle tend to move along them in a coil fashion over here. Now, what's the problem? Why haven't we been able to achieve it? So just like in the case of sun, if you see the solar winds and solar flares basically give rise to these instabilities. We have similar instabilities in these machines as well. How do we study them? So that's wherein we basically go into simulations, and typically what we would have is a magnetic field lines in a tokamak looks something like this, which basically forms a flux surface. So this is basically different flux surfaces. This is a cross section over here. It winds around the torus to form a twisted magnetic field over here. The problem over here is typically if the flux surfaces form closed torus, then it's easy to simulate. Whereas if it forms a X point like this, a separatrix over here, we'll encounter problems. And I'll tell you why it's a problem. There are few codes which tend to simulate these regions, the outer region, the outside the X point, but they use some kind of a combination of two different codes at the interface. We want to avoid it. So that's wherein we are going to use a neural network to perform this. And machine learning has come into experimental fusion for a long time, and there have been quite recent results, as well as in simulation, people have started using machine learning ideas. So today I will try to demonstrate to you how a neural network can replace one of the modules in the actual plasma simulation itself. So to start with, basically what we are trying to do is in a plasma simulation, we are trying to do a kinetic theory. We are trying to solve kinetic equations over here. This is what is referred to as Vlasov-Maxwell equation, basically Liouville equations along with the electrodynamic equations over here. And to solve this, typically we do a particle in cell simulation. Here we have both particles as well as fields. Compared to say for example MHD simulation. This is a cartoon wherein you have multiple particles within this domain and grids, which cross-sectional grids. So the particles move within this domain, and then they basically give rise to charge on these grids. The grids on the grid we can solve for the electric field, and that electric field will act on this particle and move the particle, so that we get the complete cycle of the particle in cell cycle. So basically we start with over here, this is a simpler grid with particles, and you accumulate the charges, find the density at the grid point. From that you update the field, by that solve the Poisson's equations, get the electric field, find the electric field at the particle position, and then that generates the force. That's how you can basically simulate these things. This is different from a typical MHD simulation, wherein MHD will need collisions over here, as well as MHD doesn't capture some phenomena like Landau damping and so on. So, okay. Moreover, you will find that it's not just a simple particle in cell, we also have a strong magnetic field, right? So that leads to, so it's a 6-dimensional problem to start with. It's a phase space problem, but because of this applied magnetic field, we can actually reduce it into a 5-dimensional problem, which is much better to work with. But the problem is then we have to keep track of this magnetic field, the geometry of the magnetic field. Now let's go into one of the problems that we solve using the neural network. So let's take this particular case wherein a particle is sitting in a bulk over here, and we want to project this particle along the field line. So we have two of these planes. We want to perform simple interpolation. Now the typical Euclidean interpolation doesn't work, because we know that the particles move much faster along the magnetic field. So we want to capture that effect. So we will have to project the particle along the magnetic field and perform interpolation using that. If it is a simple 2D interpolation, we can always do this using some kind of area coordinates, using this kind of formula. Whereas in this particular case, we'll have to move along this field line. So one way to demonstrate this is if you take one of this toroidal cross section, open it up, just like in the case of solar flares, if you see they'll trace out magnetic field. Over here you'll find that the density or the electric potential, they trace out this magnetic field. And what we need to do is we need to move along, make sure that the interpolation takes that into account. Now how do you do that? If it is in the core region over here, you don't, as long as you don't cross this X point, it turns out that you can map this into a Hamiltonian system and then write down an action angle variable and convert this, map this into a straight line field coordinate system, wherein the magnetic field lines can be mapped, defined. We can define a coordinate system such that it becomes straight lines, the magnetic field. So once that is done, it's very easy to perform this calculation. Whereas if you try to cross this X point over here, you'll find that you will encounter a singularity. So how do you avoid this? How do you avoid this coordinate transformation? So instead of that, what we end up doing is we perform numerical integration. So given a magnetic field, we can always perform numerical integration and move the particle along the field line, but it is expensive, it is computation expensive. So instead of that, we basically replace it with a neural network, a simple neural network like this, wherein we train the neural network to predict what is the expected point at which it would project along the field line. For this, we basically use the data that we get from numerical integration, which is a very costly affair over here. But then once a prediction is done, if we manage to train it, which is nothing but a simple function fitting, okay, the neural networks acts as a universal function approximator over here. And once we train it, we manage to go from a particle position in one shot, in one step to a projected point over here. Once that is done, we are able to perform this interpolation. Now, I know there are a lot of critics about neural networks and machine learning. I should point out that it turns out that the convergence and existence was studied by none other than Kolmogorov and Arnold back in 50s, basically prove the existence and convergence of these kind of functions. Luckily for us, we basically use the exact same neural network that they kind of assume, or the structure that they assume, and we find that our estimation. So this particular plot basically shows what is the expected RZ and what is the estimated. So here 45-degree line basically says that that's the exact match. Any deviation from it is the error. Over here you can see that it gives a very good approximation, and with the error of less than 3% in this particular case. So we have managed to capture the magnetic field configuration using a simple neural network. We have managed to replace this computationally expensive process module with a simple neural network. Now we move on to trying to prove to the community that yes, this works, right? So the way we went about it is to show that first of all, there are codes which work in the core region. So we perform this simulation of ion temperature gradient mode in the core region. We basically take this core region, build a grid over there, add this experimental profiles, temperature and density profiles, and then move on to perform the simulation and show that as the simulation runs, it develops this instability, which is referred to as ion temperature gradient instability. And we are able to show the localization as well as the exponential growth. This is a proof of principle to the community that yes, just by replacing this coordinate transformation by a neural network does reproduce the results that is expected. And further to show how the structure looks like, this is the electric potential. You see that it manages to capture the magnetic field lines structures over here, and this is a 2D cross section, and you can we further do mode analysis to show that the experimental M and N. So over here you can have mode numbers in the cross section as well as number of times it twists around. So we are able to capture those values same as the experiments in this particular case. Overall, to conclude, we have managed to build this G2C3 code which is developed completely at IISc. It's a particle in cell code, and it makes use of various experimental data and different configurations, either from IPR, Ahmedabad, or there are other tokamaks worldwide, as well as we have a 5D version of the gyrokinetic particle in cell code. It's a MPI code. It uses PET-C libraries to perform these calculations, and we have incorporated neural network within the whole process, and we have managed to demonstrate using this microturbulence results that our code is consistent with already existing code. Now, future, we basically plan to extend it towards the region where the cross the X point and try to run the simulation and try to demonstrate the performance in that region. With that, I thank you and stop.
One quick questions. One.
Hi. There was a place where you showed that you could straighten out some of your trajectories.
Right.
Yeah. So you do it locally or?
No, this is a global wherein it makes use of the full motion to extract this transformation over here.
Okay, so it's exactly like the action angle rectification.
Yes, right. It is the action angle variable.
And this is in 2 dimensions. I mean, one action, one angle.
Right. So the reason why it's 2 dimension is the way the magnetic field is constructed. So this is all because of the way experimentally they construct these magnetic fields such that they form surfaces. This magnetic field always lies on these toroidal surfaces, and that's how it reduces to a 2-dimensional problem.
Okay.